Going live on YouTube.
Great. Hello, everyone, and welcome. We are so glad you're here. Welcome to the May meeting of the Salt Lake City R user group. We're going to make sure that everybody can get in and get settled as we're here. So as you're coming in, I believe you should be muted as you enter, but please do stay muted as this is will be a Zoom with a lot of people in it. So, we are super excited to have Chris here today. And before he gets started, we're just going to do a couple of announcements. So you probably found us via our meetup page, but I'm going to drop in a link to next month's meeting in June here. So we would love to have you join us for in June for Jeremy Allen to speak about uh, data wrangling and how to have a lot of transparency into your data wrangling workflows and how to understand how to more deeply understand the data transformations that you're doing by using data visualization during that wrangling process. We are this is a professional and friendly space, and we use the R Consortium's code of conduct here. So I'll drop that in here. So just as if we were in person with each other in a room, we expect that we all treat, each other with professionalism and courtesy. And Andrew, me, and Mark will be moderating this meeting the way while Chris gives his talk. So we're really glad that you're here, and we want to make sure this is a space that is meetings that are professional and of high quality. So next month's meeting in June will be like the last one for the spring, and then we'll take a break in at least July, and then maybe come back August, maybe September, something like that. We are super interested in having folks from our community speak. So if you have, a package that you recently learned how to use, or a project that you've been working on that you think would be of interest to the larger community, we'd love to have you reach out to me or Andrew or Mark, and we can talk to you about preparing a talk for the fall. That'd be really fun and great. And I think that's all our announcements. The other reason we'll be off in July is that USAR will be happening in July, and that is, or very late June, I think, actually, and that will be live streamed, and you'll be able to participate. And then our studio conf will be happening in July, and that also will be live streamed and free, and you'll be able to watch. So it's like there will be enough content out there June, July for us all to be learning about data science and R. So we're going to take those breaks there. But certainly if you are not connected to the orgs putting those on, I would recommend that you look out for them and join those. All right, so today I am pretty excited to be learning more about random forest models and how to understand them more deeply. So Chris Kushar is going to be speaking for us, and Chris is a data scientist at Vivint here in Salt Lake City. He has a master's in statistics from Utah State, and we are so glad that you are able to come and share with us about Rfviz, about being able to visualize random forest models. So Chris, thank you so much for joining us, and we will get you, let's let you get started.
Awesome. Thanks, everybody. I'll go ahead and share my screen. So a little bit about myself first. So me and my wife, we have 4 kids. Here's a picture of them. My oldest is Bryce. Then we have twins, Callie and Kenzie, and then our youngest is JC. We had them all pretty close, but it's a lot of fun. So I work from home, so you can imagine my coworkers when I leave my office, what it's like. It's like pure pandemonium. They have like play tunnels, Barbies, Legos, whatever. So, on Friday when I peruse the office, it's more like peruse and make Lego dinosaurs or something. But anyways, talking about what you're really here for. So Rfviz, it's an interactive visualization package for interpreting random forests in R. And I will go ahead and share my screen. Oh, you guys can't even see my screen yet.
We can see the your browser right now, and it looks good.
Okay. Oh, sorry. I'm sharing a picture right here too. Can you see this?
Yeah, we saw that. Yes,
Oh,
yes.
you
They
did.
are
Oh, okay.
adorable. So adorable.
Okay. I just thought I was like talking to the camera without sharing.
Yeah, you're good to go.
All right. So Rfviz is an interactive visualization package for interpreting random forests in R. And it comes from the original creators of random forests, their algorithm and their implementation in Java. So when I was in my master's program, I had the lucky opportunity. I worked with Adele Cutler for my master's at Utah State. And so Dr. Adele Cutler and Dr. Leo Bryman, they created random forests back at UC Berkeley. And a part of their package, what they did was they created a plots in Java that allowed you to visualize and interpret random forests. So if we click this link here, you can see their original plots in Java, how they looked. They used what are called parallel coordinate plots. And it allowed you to visualize how the trees were classifying or regressing different data. And when I worked with her, I was able to, she wanted me to translate them into R. So I made the R package Rfviz, which is just a direct translation of their Java work. And I'll skip, if you want to read the Torrance data science articles, you can, but I'll skip the fluff and just go straight to the theoretical background. So for those of you who don't know what random forests are, random forests fit a number of trees to a regression or classification data set. Each tree is fit to a bootstrap sample of the data, meaning taking a sample with replacement. So some observations are included in the fit of the tree and some are repeat samples. Independently at each node of the tree, a relatively small number of predictor variables is randomly chosen, and these variables are used to find the best split, based on some metric or characteristic chosen. And then the trees are grown without being pruned or cut off, and they're grown to the whatever level you state within R or Python. And then for regression, all the observations are passed on the trees and the predictions are averaged or voted on for classification. Now, I'm sure all of you, if you're familiar with random forest, one of the main things is variable importance. So after you run your model, you look at, oh, hey, I want to see my variable importance plots, and you can see the overall variable importance. One of the key things of Rfviz is it allows you to see what's called local variable importance. Now, whereas for overall variable importance, the way it's calculated is you, for each variable, randomly permute the data and compare like the classification rate to your original model. And the difference between those is how important that variable is to the model. For local importance, it goes on a row by row basis. So let's say you take your first row. It will randomly permute the first column and see how that variable classifies or regresses for that individual row. And it continues that for each of the columns within that individual row. And then it looks at the average difference across all trees for that single observation on that single row per each column, and that becomes its local importance score. And then just to get overall variable importance is just the average of the local importance scores over all the observations. So really what this enables you to do is fine tune how random forest is classifying or regressing the data. And the reason why I'm to give a little background too. So each one of these theoretical backgrounds is the background definition behind one of the plots I'll be showing you. And another one of the plots is called proximities. And now proximities within random forests are just the proportion of time two observations end up in the same terminal node when both observations are out of bag. So you can kind of think of it, I'm going to take observation 1, observation 2. If I'm thinking of classification, I'm going to pass it down all the trees and see how many times they ended up in the same terminal node across all trees. And that becomes how similar those two observations are to each other within random forests. And so the proximity score, you can obtain it for all the pairs of observations, and then it gives you just a proximity matrix, which then I use to create a different plot. And so the style of plots that we'll be looking at are called parallel coordinate plots, and they're used for plotting observations on a handful of variables. It can be discrete, continuous, categorical. Each variable has its own axes, and these are represented as equally spaced parallel vertical lines. And I'll show you what this looks like. Just as a, so this is what we'll be looking at within R today. So we'll be looking at a parallel coordinate plot of our original data, a parallel coordinate plot of the local importance scores, and our proximities. And the key with the proximities, I'll scroll up a little bit again, is when we look at it, we're not looking at the actual matrix of, you know, if your data set has 100 rows and 100 columns, 100 columns, you would be looking at 100 by 100 data set, right? But for here, it uses principal component analysis. Let's remind me tomorrow. It uses principal component analysis to take the first three principal components, plot that on an XYZ scatter plot, which then allows you to reduce the dimensionality, but still see the differences between the data. And so I'll share now what we're probably all waiting for. You've heard me blabber on enough about the theory, but just for our intents and purposes, I thought it was necessary. So I have a few examples we'll be going through in R today. And I can share this code file afterwards if you all want. So the main library, you know, it's the Rfviz is within CRAN. So you can just do an install.packages of CRAN. You can also get it from GitHub too if you want. So let's install our libraries we need. The first example we'll be looking at is the breast cancer data example. Now this one's just from the UC Berkeley machine learning repository. If we look at what that data looks like, you can see all the different columns we have, anything from clump thickness, uniformity of cell size, all the way to what class it is, whether it's benign or malignant. And this code here, I separate the data into our feature variables and our response variable. And this is our RF, I call it RF prep within the Rfviz package. So this function runs default random forest and it prepares it for the plotting function all automatically. And so I'll show you what it looks like after you run this. So it just runs regular random forest, and you can do RF prep $, and you can get your original random forest output. But then it also includes the data set formatted for the plotting tool. So for this example, I kind of wanted to show, let's say we look at our variable importance plot. Let's see if it'll let me zoom this. Oh, it's blank. Cool. Let's try this again. So we can see our overall variable importance that I was talking about a little bit earlier. Making it wider made it worse, I feel like. All right, there we go. So we can see, your standard output that many of you probably have seen within R. You can see let's look at the mean decrease in Gini plot, for example. We can see that uniformity of cell size and uniformity of cell shape are most important to the prediction. But let's say you wanted to see specifically what was most important about those predictions for each class. You can pull up the visualization tool using this function. So Rfviz of your prepared random forest data. And we'll be looking at the 3 plots. Let's let this load for a sec. So my monitor is a little bit small, so let's see, I need to make that, I don't want it to go full screen here. So it might be hard to read the variable names here. But if you have a bigger monitor at home, you can easily make it wider and you can see them all. But you can see it goes from like clump thickness to mitosis, which if we look at the head of the data again, you can see it just follows that order. But here's what it looks like. So you have an inspector here on the left that you can interact with the data with on the plots. We can see here's an input data parallel coordinate plot, and the axes range from the minimum to the maximum. I've talked about the developer who's originally behind this technology, and they don't want to add the tick marks because they felt like it would clump up the plot and make it really hard to see. So for our intents and purposes, just think of this as the minimum of that clump thickness, the maximum of the clump thickness, and all the values in between. Same with the other columns. We can see over here on the right, we have our local importance scores. Each one of these lines in the parallel coordinate plots is an observation in your data set. And down here on the left, we have our metric multidimensional scaling proximities, or the first 3 principal components of the proximities matrix, plotted on an XYZ axis. And if I press R on my keyboard, I can enter rotation mode and see the different directions it goes based on my XYZ axis. Now here's where the fun starts. Let's say I'm interested in this clump of blue data here that seems to be separated from the rest of the data. What I can do is I can click the plot, drag my mouse, and select that data. And now you can see if I select just here, it'll select all the other columns as well. It selects it within the proximities plot too, as well as the input data. And now I can go back within R and I can say, hey, let's see what that data was that I just selected. And I can see it over here in my console on the right. Let's say I wanted to know just what class it was. I can actually save it as an object in R. And I can look at the summary of that data for the classes. And you can see what I selected was mostly malignant. And if we were able to see all the column names, you would see that this column here is uniformity of cell shape. And so I can look at that and see the summary of the data I just selected right here. I can look at the summary of the uniformity of cell shape, because random forest is saying that higher values, it has higher importance, these values of uniformity of cell shape to the prediction, which essentially this is just visualizing our overall variable importance for uniformity of cell shape right here. Because if I go back to the variant plot here, you can see uniformity of cell shape was the second most important to the mean decrease in Gini. And we can then see what those exact values are. And it's for the malignant class. You can see it has a median of 6, a max of 10, a minimum of 1. you can see that the majority of what we selected was the malignant class. But I can also say, if I want to compare, all right, let's take what I just selected. Let's get rid of it on the plot. I can click this deactivate button here. And so it will temporarily be gone from the plot. I can reactivate it if I want. But the trick here is I can deactivate it, select the rest of the data more easily, go back within R, and I can store it as an object again. And wow, look, that uniformity of cell shape, it has lower values. And you can see it's mostly benign. So visually, we're able to recognize, hey, random forest is saying these guys are locally important to the prediction. Their overall importance is pretty high for the mean decrease in Gini. We can then drill down pretty quickly to say, hey, this is what those exact values are. And, you know, granted, you might be able to say, hey, this data set only has 2 classes. You could easily just look at the overall variable importance and then look at the summary within the 2 classes yourself. Yeah, that could definitely work here. But let's say you have a different data set, and that leads me into my next example. If you're all familiar with the GLASS data set from the UCI machine learning repository, it has different minerals or elements, and it has 6 different classes. So let's say we were looking at this example and we wanted to see quickly differences between the data and what's most important to the predictions or the different predictions of the classes. We can again run our prep function with our feature variable and our response variable. We can look at our, let's try this again. I'll zoom in. You can see the variable importance plot for overall. You can see, you know, magnesium is really important. Aluminum, barium are very important to the increase in node purity. Then we can drill down again using our plotting function. And this one looks a bit cleaner just because of the way the ranges of the data are. And let's so if we look here, you can see, you know, you can easily see the column names better. You can see the colors of the different classes. Now, just by looking at this right off, you might say, hey, let's look at the, you know, what I do is I try to say, hey, let's see if I can find some easy differences between the classes and the local importance scores. Now, if I look at, let's say, magnesium here, you can see for this yellow class, these values of magnesium, which correlate with, in all actuality, low values of magnesium, are very important to that prediction of this class. And we can look at what this data is. Let's see what, I'll make this small again so we can see this. Let's look at the summary of that data. Oh, you can see it is mostly, it's either type 6 or type 7. And we can see what, you know, it's mostly type 7 when we look at the data. So by using the local importance score plot along with the input data, you can see that low values of magnesium and medium values of even sodium are very important to the prediction of type 7. We can then look at what those exact data points are. You can see it here, or you can look at the summary. So you can see that mostly it's like magnesium values of 0 or sodium values of 14 give you mostly type 7. And so where I find this useful is you can easily drill down on your overall importance for a number of classes. So whereas this has 6 different classes, you can easily drill down and say, hey, for this specific class, even though I'm not looking at overall variable importance anymore, for magnesium, we can see which class is most important to and what values are most important to that prediction. Let's try another one. Let's say we wanted to use our proximities plot down here. We can rotate the plot and see, hey, look. And as a reminder as well, this plot basically is showing us how random forest is grouping data together across all the trees. So you can see, hey, this yellow class, random forest, is grouping it together. And it seems to be getting pretty good separation among the classes.
Can you remind us what that principal component plot, what's the input to that? Is it the features or is it something else?
Yeah, so it's the proximities matrix, or the proportion of time each variables or each of the observations get passed down the tree and end up close to each other,
Okay.
If that makes sense.
Yep. So it's not principal component on the features, it's like principal component projections of the how the random forest treated these observations.
Yep.
Okay.
Yeah. And so essentially it's a visualization of the random forest trees output. So, this might be kind of new for people because there isn't really another way to visualize random forest trees to this depth, I don't think. But it's free, it's out here now. Maybe you guys have heard of like IASD, where you can see different clusters of data. This is, I would say that's the most similar thing to it, is this R package, but this is free, you don't have to pay. And I will show you another example now, kind of a different style. Let's say you're thinking of like an unsupervised clustering algorithm. Let's say you want to do like k nearest neighbors, k meteoroids. You look at your scree plot. If you're familiar with the scree plot, I feel like generally it's like 3 or 4 clusters is where the elbow is. And that's how many I should do for my data, and then look at the data and see what it kind of looks like. And here I wanted to show you kind of a different method you could use using Rfviz to come up with groups of data yourself. So the first example I'll share is the iris data set. And so the iris data set is the flower data set. And it has 3 different species: Setosa, versicolor, and virginica. And it has 4 variables: sepal length, sepal width, petal length, and petal width. And let's say I wanted to do unsupervised random forests. And I wanted to look at the data and how random forest is treating that data. So I can use my rfprep function to say, hey, take just the columns, but don't give it a response variable, run random forest, and let's visualize it. And when you're running random forests unsupervised, you can't do importance scores just because it doesn't have the original classes to look at. Let's see, maybe I'll just make this wide. Yeah, there we go. So we can see our 2 plots that we have available here, our input data and our proximities plots. And we can see that it doesn't have color because before the colors matched up with the classes, but here we don't know what the classes are. And so where this can be useful is, let's say instead of doing clustering, I wanted to say, hey, I actually just want to find groups in the data that are similar to each other visually. I could look at either of these plots. I can press R to go into rotation mode, press R to go out of rotation mode. You can see how random forest is grouping the data together. And it looks like there's a pretty distinct grouping right here. So let's select it. Now it highlights what's in the input data plot. We can see that it has low values of petal length, low values of petal width. It seems to have higher values of sepal width compared to the other data. We can go back within R again, and we can say, hey, what I'm selecting right now, let's store as a variable. And let's look at that data. And we can see the summary of that data as well. And you can see that it's the Setosa species that random forest grouped together there. So kind of cool, right? You can see how random forest is saying, hey, this is a distinct grouping. And you look at that grouping and it happens to be all the Setosa species. So let's say I wanted to get rid of that data and look at this other grouping. It kind of looks like there's two distinct groupings. I don't know. Maybe if I split it down the middle. Let's try that. Go back within R and say, hey, this is what I selected right now. Oh, look, it's the versicolor species. And we can see the summary of that data, how it looks. Let's look back at that input plot. Oh, look, it has lower values of sepal length, sepal width, petal length, and petal width compared to the rest of the data. Now, if we get rid of that, we can just select the rest of the data, see what it looks like. Oh, look, it's mostly the Virginica species there. So this example is kind of straightforward just because it's the iris data set. There's only 3 classes. It's a classic data set that people use for examples. But let's say we had more classes again. An example from the UCI machine learning repository is the fish data set. Oh, and of course, my live demo, I did the path wrong for the file. Let me fix that real quick. I'll just set my working directory as my downloads. Session. Oh, I think it's right. Set working directory, choose directory, downloads. There we go. Let's try that again. There we go. Looks like it downloaded it this time. I can look at that data, see what it looks like. It has our species of fish along with some measurements of the fish. Weight, length 1, length 2, length 3, height, and width. And these refer to like the fin lengths along with like the length of the fish. And so you can see there's 1, 2, 3, 4, 5, 6, 7 different species of fish here. And let's say I didn't know the fish species though. I just knew all the weight, lengths, and height and width of these fish. What you can do is put it back into the RF prep function, run Rfviz here. And let's make this wide again. And up, clicked wrong. Let's bring this up so we can look at it. And so you can see again, here's our input data plot, which again is just each row of the data is a line, and each dot down here correlates with one of those observations. And it kind of looks like a spiral if you look at this proximities plot. Kind of cool how it did the PCA in the three-dimensional view. But let's try to figure out some interesting groupings here, not knowing the species, but we also know them ahead of time. Let's just select a grouping right here. Let's see what that is. You can see how it correlates with low measurement values in comparison to the rest of the data. Let's see what it is. So you can see the summary of the data, the different measurements. Let's see what the actual species is. Oh, and it looks like for some reason it's not reading in, it's putting it as a character. Let's try this instead. Oh, so you can see it's like a combination of roach, parky, perch, and smelt. Seems to be like a little bit over half is smelt. Let's look at it by the input data plot. Let's look at these high values right here. And we can see how it kind of groups the data down here. Let's try this again like this. And here's another trick that you can do. Let's say you want to move this plot while looking at that same data. It deselects it automatically. But you can come back to this inspector and say, hey, I'm going to turn all those guys I selected green. So now I can rotate it and say, hey, look, it looks like it grouped all those guys with high measurements of height along this edge here. We can see again what that data looks like. We'll look at our second grouping. Oh, looks like it. Oh, yeah, because I'm not selecting it. So in real time, you have to be selecting it. So I could go back in and select that data. And you can see the various weights, lengths, height, and width. Let's look at what species that is, since we know it on the back end. Oh, you can see the like mostly bream there. But you guys get the idea, right? Instead of using a like k-nearest neighbors and look at the data that way, you could, like I'm a very visual person. So I could visually select the data of how it visually is higher or lower than the rest of the data, or how it looks on the proximities plot. And I can go back within R and say, oh, that's what this grouping looks like. And I looked back at the species just for this example to kind of show, hey, in the unsupervised case where you don't know the response variable, random forest is going to be able to show you distinct groupings of data. And they're meaningful because here we're able to identify without knowing ahead of time various species. Let's try it again. Let's say I select this grouping here. Let's just overwrite this. And you can see that's all pike there. Let's select something here. Let's just try the middle right here. Let's see what this is. Mostly perch and some roach. So I hope this kind of makes sense to you guys on what you can use random forest for. So, you know, you can do your normal prediction model. And then if you're really curious as to how the data is different from other data based on the variable importance of the local importance scores, or if you want to use the unsupervised case, you can use it however you want. It's available within CRAN, free for you guys to use. I think I just open it now for, are there any questions that you guys have?
Yeah, thank you so much, Chris. That was really interesting. There's some comments here about like having seen those kind of plots, but not being like actually sure what are they saying. So that was it was really, really interesting. So if you have a question that you want to ask, you can either type it in the chat, or if you use the raise hand feature in Zoom, we can you can unmute and say if you have a question. I think so. I'll kick it off and say. Some of this, like the variable importance, like say like the local variable importance, or some of these measures, they seem to be like you're measuring variable importance with something that's a lot about um, like purity or Gini coefficients. And I noticed that the variable importance is pretty different if you're just looking at like measures of predictive performance. Like often like the second most important thing will be quite different. If you're looking at the the metric, like how do you assess variable importance, right? Like what do you look at? Do you look at something that's about purity or something that's about performance? And I was wondering if you could like if you've explored those differences, or like why for the issue of understanding random forests is the thing that's more like purity more the important thing. I was wondering if you could talk a little bit about like the ways of measuring variable importance and how that affects what you learn about the model.
Yeah, sure. Yeah, the main one I usually look at for classification is just Gini, just because when we're thinking of classification, right, we want to be able to classify between, let's say, two groups as best as we can. And Gini is just a measure of how well at each split the data is pure, meaning let's say I have two classes, I do one split, I look at those two nodes on the split and say, hey, how much are they one singular class versus how much are they like 50-50 each class? And so with classification, I'll look at Gini. Maybe I'll just pull up these var-int plots again. I think I just showed only classification examples today. Let me show you a regression example. Can't remember if it's here.
I think the first one was regression.
Oh, was it?
The Oh no, the second one. So that one, so breast cancer was the glass one is regression.
It was still just
Oh,
different glass types.
oh
Let
yeah.
me, I think I have a regression example within here. Yeah, here you go. So within the Rfviz like documentation, here's a regression example, and it uses like the MT cars data set. So let's say I run my regression. I can look at the var-int plot of this. And here, the main one I look at for regression is the difference in mean squared error. And what that essentially is let's say I do my first split. And what it does is it stops the model there. And it says, hey, how much based on splitting for this variable, I think this is weight within the MT cars data set, is if I stopped it there and I used that for my prediction, if that was my terminal node, what do the predictions look like? And then it compares it to the randomness of, let's say I randomly permute this variable instead, and you can see what the percent difference in mean squared error is across all the trees and all the splits. And I think just for overall variable importance, it'll look at the very terminal node to say, hey, let's look at the percent difference in how accurate we are to our response variable. And so that's why I use it here, because it kind of matches up with what you're looking at. When I'm looking at regression, I want to minimize most of the time like mean squared error or get my prediction as close as I can to possible. And I wouldn't really look at the increase in the known purity just because I don't feel like personally it applies here, because we're trying to get as close as we can to a continuous value rather than trying to get known purity.
Yeah. And so when you were showing the interactive plots, the panel kind of on the right talked about variable importance. Um, so what kind of variable importance is that? And there's a question here from Kyle about like, is there a way to specify what you're using for variable importance? Like, we've looked at a couple of different things here, or people are interested in other things like SHAP values.
Yeah, sure. So I don't know if you can do SHAP with this, but just like when you do your normal random forest function, you can specify the criterion, right? You could say, I forget what it is. So, well, I'll back up. Rfviz just uses the default for random forests for the splitting criteria. And I can't remember what the command is in here, if there is one, but I'm pretty sure you can, I don't know for sure, guys, but I'm pretty sure you can just say what your splitting criteria is, whether it's Gini or mean squared error or etc. And I think it's just in the documentation for random forest here. But what you can do is any random forest function that you want to include within RF prep here, you can just add it. So I could do mtry equals 10. I could change the sample size, and any of these will automatically feed into the random forest. So does that answer your guys' question?
I think so. I think
Yeah.
so. Like how we can change those different things.
Yeah.
So there's a question from Alexandros about it's cool to see these interactive plots, and it sounds like it was built like those interactive plots are not built like directly with R. Is there how would you go about either customizing those plots, or did you ever think about using Shiny for this instead of the like what's kind of out there, like what's possible in terms of configuring them, or say changing the dimensionality reduction method, or getting sort of like a shiny like experience where you have a lot of control.
Yeah, sure. So you can change anything you want, really. The source code is available on my GitHub, and I'll just show you. Oh, I'm not logged in on this one. Maybe I can search it. Rfviz GitHub. Yeah, there we go. I'm going to pull this other window up. If it'll let me drag you. Come on, Chrome. There we go. So within my GitHub here, you can grab the data yourself if you want, or the source code. So I'll just put it in the chat if whoever wants it. But you can look. I'll show you, for example, if you wanted to change the PCA. I think it's in here. Let's see. Nope, other one has to be. Let's do this one. Excuse me. So this is the source code. It uses another package in R called Loon, which I'll show you what this is too. These guys from Canada made this package that I built mine on. It's based on TCL TK or Tickle TK code. So I've looked at doing it within Shiny, but there's not very many ports from like TCL TK to R Shiny. I mean, you could try. I bet someone, if you know how to do it, I bet you could do it easy. I couldn't figure it out though, so I just built my own. But here's the source code for it. For example, if you come down here, here's where it does the principal component. So you can change whatever you want and feed it into the plot yourself. And they provide some pretty good tutorials on, let's see, they have some documentation here, I think. Yeah. And they show you all the different ways you can use interactive plots that they have available, as well as the help. They have some guides on how to learn, how to build your own. And I can add this to the chat as well.
Awesome, thank you.
Yeah.
Let's see, we're coming up on the end of the hour, but there's a question here about um, like like actually visualizing trees. So, we probably have all like had classes or seen tutorials where you like visualize like a single decision tree. And what so why are like when you build these kind of visualizations, are you are we looking at these kind of plots, right, that look at like what drives the prediction, or like how pure are the nodes, or like how did the random forest behave? Like what are the benefits you think of doing something like this versus trying to make some kind of visualization for the tree structure of a random forest model?
Uh, I think the benefit here is, let's say you do like 20,000 trees. Every single random forest tree is going to be different. And so I'd say that'd be, like maybe there is a way, I just don't know. But I feel like that'd be very difficult to explain to somebody. Like, hey, this is how all 20,000 trees are looking. Whereas you could, like, if it was me, I would just use a visualization to say, here's how the output of all the 20,000 trees are looking, just because I feel like that's what stakeholders care about anyways. But not to say some wouldn't. Like, I guess it just depends on what you want to do. Like, if you want to show the output of trees, you could. I think there's ways out there that people have created that would work really well. It just depends on what your stakeholder wants. Like, if they want just the output, or if they want to see like how the output of a random forest is affecting it versus how they're visualizing. I think it just depends.
Yeah. Yeah, I think that makes yep. This person just pointed out and just agreeing, and that the you can try to like make a representative tree. Like there are methods for trying to do that, but it really depends on like what it is you're trying to do. Let's see. There was a question about like memory issues with Rfviz, and I guess it sounds like Rfviz builds very strongly on random forest. Have you ever looked at something like Ranger or the alternative implementations in R for random forest, and like what how extensible is this right now, or what kind of work have you done that on in the past in terms of like more performant random forest implementation?
Yeah, I haven't. I've used Ranger. I really like it. It's really fast, and I like the bar it shows you of, oh, this is how far you are on where you ran a forest. I haven't used like RFIz with it. I'm not sure if they have like local importance scores. A lot of other random forest implementations, like especially in Python, I don't think it like. I tried to see the random forest in Python to see if it has local importance scores, but I don't think it does. I think I just have to look deeper at it.
Yeah.
That's about the level I've looked at it.
Yeah, sure. That's great. All right. So I think there's a question about on the proximity plot, um, to, maybe like get that data out so that you could then cluster that data or something. Like, is it possible to get out um, the results of the dimensionality reduction so that you can then, say if you wanted to like cluster actually in that projected space?
Yeah. So going back to this source code here. Now let's say, I think I have to put the package into, I don't remember. To get the PCA on the dimensionality reduction, I could just do, let's see if this function's available. If I have to, oh, yep, it is. All right, sweet. So if I run, let's say that breast cancer data set again, and within the RF, this is what makes it nice, right? Like I can go RF and then see my proximity matrix here. You can actually whip that out in R and see what it looks like. And then you can run the principal component analysis yourself here and get the results of that. And you can change it how, like you could then do like k-means or whatever the function name in R is. I can't remember what it is. But yeah, you could do that. That's how you do it.
Nice. Awesome. All right. Well, I want to say again, thank you so much, Chris, for sharing this. It was really great to see these like interactive visualizations and understand more about random forests and how they work and how they behave. It's really cool to see that. We appreciate that
Yeah,
so
sure.
much.
Yeah.
And thank you to everyone who came and participated today. And thanks for your attention and your questions. We're really glad to have you. And we will be glad to have you join us again, perhaps next month. So thank you all again so much for coming, and we will see you soon.
Yeah. Thanks, guys. See you later.